Welcome to Talking Machines by Sue Park, the podcast where we talk machines, the bots, and the hottest AI papers off the press to demystify the world of artificial intelligence research. I'm Vic, and with me today is my lovely co-host, Alex.
Today we're diving into a fascinating paper that introduces the Dynamic Cheatsheet, or DC for short. This framework aims to give language models a persistent memory at inference time, allowing them to retain and reuse insights from previous interactions. Imagine not having to reinvent the wheel every time you face a new problem.
It's pretty wild when you think about it. Current language models often treat each query like a fresh start, but DC changes that by enabling them to store strategies, code snippets, and other useful insights. So, instead of just responding in isolation, these models can build on past knowledge, making them much more efficient.
Right? The paper presents some compelling results too. For instance, when Claude 3.5 Sonnet started retaining algebraic insights during math exams, its accuracy more than doubled, and GPT-4o saw its success rate on the game of 24 puzzle leap from 10% to an astonishing 99% after figuring out a Python-based solution it could reuse.
That's a massive jump. It's like giving the model a toolbox of solutions it can pull from whenever it encounters a similar problem.
Exactly. Plus, the way they structure the memory is clever. Instead of just dumping everything it has ever learned into a giant text blob, DC focuses on curating useful, transferable snippets. This means the model can learn from its successes and mistakes without the risk of getting bogged down by irrelevant data.
And it's all happening without needing to fine-tune the underlying model parameters. So, it's lightweight and practical, especially for black box systems like GPT-4 or Claude.
That's such a smart approach. It really aligns with how humans learn, building a mental library of strategies instead of starting from scratch each time.
Absolutely. The implications for complex reasoning tasks are huge. By continuously refining its memory, the model can not only improve its performance, but also reduce repetitive errors.
And I love that it's all done in real time. The memory updates happen right after each query, allowing the model to adapt and improve on the fly.
Right. And it brings up a lot of interesting questions about how we can further leverage this type of memory in AI systems. What do you think could be the next steps for this research?
Well, I think exploring the balance between memory efficiency and the quality of retained knowledge could be a great avenue. How can the model ensure it's not just keeping the most recent memories, but also the most relevant ones?
That's a great point. It'll be fascinating to see how they tackle those challenges as they develop this framework further.
And speaking of challenges, the paper also touches on the limitations of smaller models when using DC. It appears that while larger models like GPT-4 and Claude 3.5 benefit significantly, smaller counterparts struggle to leverage this memory effectively.
Yes. It's like they need a solid foundation to build upon. If they can't generate quality outputs initially, the memory they store will just be flawed attempts.
Exactly. So, it raises the question of how we can enhance smaller models' performance so they can also take advantage of memory mechanisms like this.
And it's a delicate balance, isn't it? Ensuring that the memory remains clean and free of errors while still being adaptable enough to incorporate new insights is crucial.
Definitely. The potential for iterative learning and adaptation in AI is exciting. This kind of framework could revolutionize how we approach problem-solving in AI.
Absolutely. I can't wait to see where this research leads. So what do you think? Should we dive deeper into how the memory curation process works?
So, diving deeper into the memory curation process, the paper outlines a few strategies they propose for keeping this memory both relevant and effective.
Right. One of those strategies revolves around the concept of memory pruning. It's all about identifying which memories are the most useful and discarding the rest.
Exactly. It's like spring cleaning for data. If a memory doesn't contribute to performance, it's better off being removed. They talk about using certain metrics to evaluate the relevance of stored memories based on recent tasks and performance feedback.
That's quite clever. It's almost like they're using a feedback loop to assess what stays and what goes. I wonder if they implement a threshold system for this pruning, like if a memory hasn't been referenced in a while or hasn't led to improved performance, it gets the boot.
Right, that kind of dynamic approach could help keep the model from getting bogged down by outdated or irrelevant information. It's a balancing act, though. You don't want to prune too aggressively and lose potentially useful insights.
Totally. There's a risk of losing context that might come in handy later. The paper mentions a way to tag memories with contextual information, so even if they're pruned, you have some record of why they were stored in the first place.
That's smart. It adds a layer of transparency to the memory management process. Plus, it could help the model learn from its past decisions, making it smarter over time.
Speaking of learning from past decisions, they introduce an intriguing mechanism for incremental learning. This allows the model to adapt its memory based on new experiences without completely overwriting previous knowledge.
Yes, this incremental approach is key, especially in real-world applications where data is constantly evolving. It's like instead of doing a full system reboot every time there's new information, the model can integrate updates seamlessly.
And they back this up with some experimental results. When they tested the model with and without this incremental learning capability, they noticed significant improvements in performance on tasks that required nuanced understanding.
That's a powerful demonstration. It really shows the potential of a memory system that doesn't just store information but actively evolves based on its utility.
Exactly. And what I found fascinating is how they managed to quantify the performance gains. They used a series of benchmarks to measure the effectiveness of the memory in various scenarios, which adds credibility to their claims.
That's essential. It's one thing to propose a theory, but backing it up with data is what really solidifies the argument. I imagine they had to carefully design their experiments to isolate the effects of the memory mechanisms from other variables.
Absolutely. They detail their experimental design in the paper, explaining how they controlled for different factors to ensure a fair assessment of the memory system's impact. It's quite methodical, which I appreciate.
I love that they didn't just throw numbers at the wall to see what sticks. Instead, they laid out their entire methodology, which really helps others understand how to replicate their findings.
And that's crucial in the research community. If someone else wants to build on their work or even critique it, having a clear methodology allows for better discussions and developments.
Right. Plus, they also explored different configurations of memory size and retrieval mechanisms to see how those factors influence performance. It's interesting to think about how tweaking these parameters can yield different results.
Definitely. The interplay between memory size and retrieval efficiency can lead to a lot of nuanced outcomes. I wonder if they found any sweet spots where the model really excels.
That's a great question. They did mention some optimal configurations where the balance between memory size and retrieval speed led to the best overall performance, but I'd love to dive deeper into those specifics next.
For sure, those insights could be critical for anyone looking to implement similar systems in their projects. The trade-offs involved in memory management could be a game changer for efficiency.
Absolutely, and it's not just about performance, it's about making the model more intuitive and human-like in its learning process. I think that's where the real excitement lies.
Yes, it's like giving AI a way to grow and adapt in a more organic manner, rather than just being a static repository of information.
Right, this could lead to a whole new wave of applications where AI can be more responsive to its environment and user needs.
And I can't wait to see how that develops. Shall we explore those optimal configurations next?
The implications of this memory curation process are fascinating, especially when you think about how it could redefine our interactions with AI. It's like giving the model a second chance at learning, right?
Absolutely. The ability to retain useful strategies while discarding less effective ones means the model can continually evolve its problem-solving abilities. It's a significant step towards more human-like learning processes in AI.
And the fact that this occurs without modifying the underlying parameters is crucial. It keeps the computational overhead low, which is a big win for applications in real-world scenarios. Imagine deploying these models in resource-constrained environments. This could be a game changer.
Totally. The lightweight nature of the Dynamic Cheatsheet framework means that developers can implement it with minimal fuss. Plus, it preserves the black box nature of these models, which is essential for using commercial APIs like GPT-4 or Claude.
Speaking of practical applications, the results they shared in the paper are striking. For instance, GPT-4o went from a mere 10% success rate to 99% on the game of 24 after implementing the memory mechanism. That's just mind-blowing.
I know, right? It's almost like watching a student who struggles with math suddenly discover a method that clicks for them. Once GPT-4o found that Python-based brute force solution, it was game over for those pesky arithmetic errors.
Exactly. It highlights how effective memory retention can streamline complex problem solving. I wonder, though, if they explored how different types of problems might affect the efficiency of the memory curation.
Good point. They did mention that the efficacy of DC is influenced by the model's scale and capacity. Larger models show substantial gains, while smaller models, like GPT-4o Mini, struggle to leverage the memory effectively due to their limited ability to generate high-quality outputs.
That's a crucial takeaway. It suggests that for memory mechanisms like this to be truly effective, the foundational model needs to be robust enough to produce reliable solutions in the first place.
And it also raises questions about how we can enhance smaller models to benefit from such frameworks. It's like they're saying, we're here, but we need a bit more help.
Right? They're sort of in this catch-22 situation where they can't improve without a solid starting point, but their limitations prevent them from reaching that point. It's a tricky balance to strike.
And the way they've structured the memory system to avoid context ballooning is also noteworthy. Instead of just piling on data, they focus on concise, transferable snippets. This approach not only keeps the memory manageable, but also enhances the model's adaptability.
Absolutely. It's like decluttering a workspace. The more streamlined it is, the easier it is to find what you need when you need it. This system enables the model to access high-value insights quickly, which is essential for efficient problem solving.
Plus, the distinction between their memory curation process and naive full history appending is critical. Full history can overwhelm the model with irrelevant data, while DC ensures that only the most pertinent information is retained.
It's a smart design choice. It minimizes the cognitive load on the model, allowing it to focus on the task at hand rather than wading through extraneous information.
I find it interesting how they formalized the selective retention process. It's not just about storing everything, it's about storing the right things. This is especially important for models facing diverse and complex queries.
Exactly. The adaptive memory approach could lead to significant improvements in performance across various tasks. It also opens up new possibilities for AI applications in fields that require iterative learning and refinement, like healthcare or finance.
And let's not forget how this could affect user interactions. Imagine a personal assistant that remembers your preferences and learns from past interactions to improve its responses. That's the kind of intuitive experience users are looking for.
Right. This could pave the way for more personalized AI applications, where the model adapts to individual user needs over time. It's about creating a more seamless and engaging interaction.
I can't help but wonder about the potential ethical implications, though. If models become capable of retaining and learning from user interactions, how do we ensure they handle that information responsibly?
That's a critical question. Ensuring data privacy and ethical use of memory mechanisms will be paramount. It's a balancing act between enhancing functionality and maintaining user trust.
Absolutely. As we push the boundaries of what AI can do, we also need to be vigilant about the implications of these advancements.
Speaking of implications, I'm curious about their experimental design and whether they considered any potential biases in their memory retention process. Did they address that in the paper?
They did touch on it briefly. They acknowledged that biases could creep in, especially if the stored information skews towards certain types of solutions or strategies. It's an area that definitely needs further exploration to ensure fairness in AI learning processes.
That makes sense. It's just another layer of complexity in developing these systems. I think it's safe to say that while DC is a promising approach, there's still a lot of work to be done to refine and optimize it for real-world applications.
For sure, the foundation is there, and I'm excited to see how researchers build on this work to enhance memory mechanisms in AI. The future is looking bright.
Absolutely. I can't wait to see what comes next.
I find it fascinating how the dynamic cheat sheet allows models to refine their memory in real time. It's like giving them a toolbox that they can continually upgrade as they encounter new challenges.
Absolutely. And the fact that it doesn't require any gradient updates is a game changer. It means we can leverage powerful models without the overhead of constant retraining.
Right. It feels like the best of both worlds. You get the adaptability of a dynamic system without the computational burden. Plus, the self-curation aspect is intriguing. It's almost like the model is learning to learn.
Exactly. It's a step towards making AI more intuitive, mimicking how humans naturally refine their knowledge over time. But I do wonder how well it can handle erroneous data in memory.
That's a valid concern. If it starts storing flawed strategies, it could lead to a downward spiral of performance. It really emphasizes the importance of effective curation in AI systems.
For sure. The potential for iterative improvement is exciting, but it also comes with a responsibility to maintain quality. It's a fine line to walk, balancing memory retention and accuracy.
Such an interesting discussion today. Thanks for joining us on Talking Machines today. We hope you enjoyed learning about Dynamic Cheat Sheet. Our goal is not to bore you, but fill you in on what's happening in the sci-fi, slowly becoming our reality era we're living in. And today, we learned about Dynamic Cheat Sheet.
Until next time, you can find us on Instagram at talking_machines_podcasts.